ます。So yeah, I will be presenting today's presentation in English. So yeah, today I will be presenting a paper titled Data Retrieval with Importance Weighted for Few-Shot Imitation Learning. Yeah, and this is the overview of the paper. So as mentioned, the paper is titled Data Retrieval with Important Weights for Few-Shot Imitation Learning. And the authors are from Stanford University, and this paper was recently published in the Conference on Robot Learning 2025, and was an oral presentation in that conference. And here are some links to the paper, such as the archive link and project page also. And a slight disclaimer that the credits for the images, figures, and tables belong to the original authors. So a brief introduction to the motivation behind this paper is that current imitation learning policies and robotics is very data hungry, and they often require a lot of demonstrations ranging from hundreds to thousands uh, per task. And this makes it expensive and hard to scale to new environments. And in the past few years, there has been a lot of efforts towards collecting large-scale data sets such as the Droid and OpenX embodiment data sets. And the motivation behind this work is that how can we leverage the large existing prior data sets so that we can quickly learn new tasks without having to collect too much new data. And what is proposed in the previous work is something called retrieval-based imitation learning. And in retrieval-based imitation learning, uh, uh, they augment the small target task dataset by retrieving relevant state action samples from large prior datasets using a learned latent representation. So what this means is that using some kind of representation learning, they retrieve relevant data that can help with learning a new task from the prior data. And there has been a lot of different works on retrieval-based imitation learning, such as flow retrieval, behavior retrieval, and also Sailor, which all uses different representations and also different policy learning methods. However, the problem with the previous retrieval-based imitation learning methods is they mostly rely on heuristic nearest neighbor distance in latent space. So they mostly just rely on L2 distance. And the problem with this is that it leads to high variance, sensitivity to noise, and also distributional bias in the data selection. So how can we solve this problem of the retrieval-based learning? So this paper introduces a method to address those limitations called importance-weighted retrieval, which is a retrieval-based method inspired by importance sampling. So in IWR, or importance-weighted retrieval, um, the method retrieves prior data not just by using distance between the embeddings, but they do it by using based on how well it matches the target task distribution. And they leverage something called density ratio or importance weight estimation. And the framework for this method involves four main steps. First is representation learning. The second part is the importance weight estimation. And finally, they perform data retrieval and then ended with the policy learning for the new tasks. So the first step of the framework is the representation learning. So first, we need to be able to learn a low-dimensional representation of the state action pairs to be able to enable efficient retrieval. And in this work, they just use very simple variational autoencoder to create a low-dimensional latent space. And why exactly they use VAE in this paper is that, so first is that it only it follows previous methods such as behavior retrieval, flow retrieval, and Sailor. And it doesn't, so this paper also doesn't want to modify the representation learning, only how retrieval is performed. So by using VAE, it already is quite has a smooth and compact latent space, and this is because VAE constrains a continuous and approximate Gaussian latent space by using the the KL regularization term. And finally, after this next part, after we train a representation learning. So how do we actually retrieve the data using this representation? What is the metric for this? So in the second part, which is the importance weight estimation, the goal is to estimate how relevant the prior data is to the target task that we want to learn, right? So in distance-based retrieval, which is using L2 distance, they only use the nearest target point, which can lead to high variance. So going into here on the right figure, as you can see here, this shows a case where as you can see here, if you only use L2 distance, the retrieval might miss a lot of target points that are actually close to the target data. However, when you use importance weighted retrieval, because it estimates the probability density of the target data, it is able to kind of also detect other data points that is close to that distribution compared to just using a raw distance. So as mentioned, the importance weighted retrieval models the full target distribution using Gaussian KDE in latent space. And the key insight here is that while nearest neighbor estimate only similarity, the important weights estimate the probability, which means what is the probability that this prior sample is going to be useful for the target tasks. And then the third part is once we have this important weights scoring, we can use this important weights as the retrieval score for prior data. And we can retrieve samples whose that based on a threshold on the importance weight. So if it exceeds a threshold, we retrieve that sample. And by using this kind of importance weight, retrieval can select data that matches the target task distribution, not only just the nearest neighbors. And another point is that it can be applied to multiple different granularity levels. So it can be either individual state action pairs, action chunks, and also maybe subtrajectories. And this step of the data retrieval and also important weights is the one that replaces L2 distance-based retrieval used in prior methods. So finally, we have the policy learning part. So after we perform data retrieval with the importance weight estimation, we train the policy using behavior cloning by co-training on a mixture of the target task demonstration, which is called DT, combined with the retrieve prior data set, which is called the retrieval. And we optimize a weighted imitation objective to be able to balance between the target data and also the retrieve data. And in next experiments, we will show that using this data, the added retrieval data, it provides more coverage of the distribution of the state action and also improves overall robustness. And the policy architecture and the training procedure are not changed compared to for all the different retrieval methods. And in this paper, they use diffusion policy. And the performance increase comes purely from just the data retrieval, not by using any kind of architectural or policy modifications. So finally, next part we have to evaluate the retrieval method. So we conduct a few different experiments here, mainly to evaluate three different research questions. One is performance. So does importance weighted retrieval improve policy success over the existing retrieval methods? Second is generality. So can the importance weighted retrieval be applied to different retrieval representations, such as behavior retrieval, flow retrieval, and also Saylor? And third is ablation. So why does importance retrieval help? And this will we will remove certain parts of the importance weighted retrieval to understand the implications of each component. And for the mental experimental setup, evaluation is done in both simulation and real world. In simulation, two environments are used. One is RoboMimic Square, which is an insertion task using a square peg. And 10 target demonstrations are given for this task. And also we use the Libero environment, choosing where 5 of the most difficult tasks from Libero 10 are chosen. And we sample 5 target demonstrations for each of these tasks. which leads to around 25 demonstrations in total. And for the real-world task, we leverage the Bridge V2 dataset using the WidowX robot. And this is done in 3 different tasks. So which is like corn, pick and place, carrot, and also eggplant. And eggplant is designated as a long horizon task. And this has a large amount of prior data contained in the prior data set. And to compare the different baselines, we have 4 different baselines to compare to the importance weighted retrieval. So the first baseline is simple behavior cloning only trained to imitate DT, which means we only train a policy using the target data. Second is behavior retrieval, which learns a VAE over state action pairs and then retrieves data based on L2 distance. And the third part is flow retrieval, which learns VAE over optical flow between frames and actions. And similar to behavior retrieval, it retrieves data via L2 distance in latent space. And the final baseline comparison is Sailors, which is a skill-based latent space, which compresses state action chunks into skill-based embeddings. And then it also retrieves based on L2 distance. So some details is that all these retrieval baselines all use the L2 distance-based retrieval, which we will compare to the importance-based estimation retrieval. And the policies are all trained using diffusion policy, which is a state-of-the-art imitation learning, a behavior cloning policy that's typically used in robotics. So the first question is, does importance weighted retrieval actually improve policy performance over the existing retrieval methods? And the answer is in simulation, it shows that the proposed method achieves the highest success rate across all simulated benchmarks. And in particular, for example, in RoboMimic Square here, behavior cloning nearly fails because it has a lot of it only has limited data, only maybe 5 to 10 demonstrations, which is not enough to learn the policy from scratch. And as shown here, the importance weighted retrieval also significantly outperforms distance-based retrieval, especially when the incorrect prior data might be actually harmful to the policy. And on libero task, it shows that the method also consistently improves over the other distance-based retrieval methods, and it shows that the performance gains are the largest when there's a lot of diverse and imbalanced prior data. And this shows where the nearest neighbor retrieval struggles very highly. And on real world results, it shows that the importance weighted retrieval also has a very good performance over all the baselines on real robot tasks and can achieve up to more than 30% higher success rate compared to standard refill methods. And it's also quite effective on long horizon tasks, such as the eggplant task, showing that better retrieval actually translates to better real world performance. And here also we show, for example, what kind of task relevance and also temporal distribution is being retrieved. So for example, when we retrieve data, is it actually irrelevant or is it actually helpful to the task itself? And for example, here on the left plot, it shows that when using behavior retrieval, which is a distance-based retrieval, that a large portion of data retrieved is actually harmful or actually not relevant to the task itself, while using importance weight actually shows that it has more task relevant demonstrations. And on the right side, it shows more the temporal distribution of the task, and it shows that behavior retrieval actually oversamples at early time steps. For example, or when the motion is actually just a reaching motion, while using importance weighted retrieval produces a more balanced distribution across the temporal phases. And this improvements makes for more informative training data. So the training data is more curated and better informed, and also has a better coverage of the different subtasks. So the second question is that can the importance weight retrieval be applied to the different retrieval representations? So for example, so here we test first we test importance weight retrieval when combined with different methods such as behavior retrieval, flow retrieval, and Sailor. And it shows that importance weight retrieval consistently improves performance when you just replace the L2 distance retrieval in these methods by using importance weighting. And the second part is we compared against different latent spaces. So not only using VAE based, but also, for example, using other alternate representation like using BOL and BOL ResNet. So, and it shows that it works based on using just VAE based latent representation. And actually, the performance gains is quite limited for non-smooth embeddings such as BOL. And the final question is, so why does IWR actually help with the posse learning? And to do this, we need to kind of do some ablation studies, such as ablation on the important weights, ablation on the bandwidth parameters, and also such as the retrieval threshold. And here we actually show while the WER compute some kind of normalization for the retrieval, we show that by removing the normalization of the prior distribution, it actually shows that the performance degrades, and this shows that the density ratio or the importance weights is actually very important for the retrieval. And in the results in table 3 also we show that when we do ablations on the bandwidth, we show that uh, IWR is robust with smoother density estimates slightly only improving performance. And finally, we also set the retrieval threshold, which is the amount of data that is retrieved from the threshold. So, for example, here in table 4, it ranges from 20% data to 60% data retrieved, and actually shows that if you increase the amount of data to 60%, too much prior data can actually introduce harmful examples. So as you can see here, from 50 to 60%, there is a huge performance jump around 34%. And it shows that the amount of data that is actually retrieved can affect the policy performance. So to summarize this paper introduces importance weighted retrieval or IWR, which is an importance sampling inspired based method for a retrieval. And IWR estimates the target and the prior data distributions, and retrieval data is based on importance weights or density ratios rather than using raw L2 distances such as done in prior work. And the experiment results showed that IWR is able to select data better for retrieval, as shown in the performance improvements in both the simulated and real world tasks, including a long horizon task. And some limitations of and future work for this paper is one is that they do not further evaluate what makes an effective latent space, and as they only largely use the VAE based latent space. And the second one is that the evaluation is largely limited to just pick and place tasks because it's very hard to collect large scale data for more dexterous manipulation tasks. So in future work, there is room for improvement on the type of tasks to do. And finally, because IWR assumes the use of Gaussian KDEs, it can be computationally intractable and also numerically unstable in more higher dimensions. So in future work, it might be able to kind of explore different alternatives for importance sampling other than Gaussian KDEs. So this concludes the presentation for this paper. And yeah, thank you very much for listening, and please feel free to ask any questions.
Okay, thank you for your presentations. Are there any comments from online or では、質問者の方から、まず質問があればお願いします。
はい。
じゃあ、小野田さん、よろしくお願いします。
May I ask you a question?
Yes.
I believe that this paper was selected for oral presentation.
Yes.
What aspects of your this paper do
Mhm.
you think were most valued for this research field?
Yeah. Okay. Yeah, I think that's a good question. So one thing is that so in robotics specifically, even if we have a lot of prior data, um, just training all of a policy on all of that data is actually not helpful. And this is a bit different to, for example, language models or maybe vision language models, where maybe pre-training on a lot of different data is actually useful. So why this paper is actually helpful is because it helps you better curate which data is more relevant and more important for policy learning. And it shifts the focus to, rather than collecting large amounts of data, we can actually just be able to curate data better and lead to better policy performance. And the good thing also about this in terms of technical improvement is that while prior works only use like the distance-based retrieval, which is very hard to determine if it's actually important or not, but here they use kind of more like probabilistic methods to kind of estimate if the data is actually useful or not. So it has a better coverage of which data is better or not for the retrieval. So I think those 2 points are what made it very important for robot learning, especially right now where data scaling is a big focus in robotics community. Yeah,
I understand.
Yeah.
Thank you very much.
thank you.
はい、ありがとうございます。Are there any questions or comments? それでは、もう一人の質問者の今井さん、お願いできますでしょうか。
すいません。今井さんは高波さんの質問者でごめんなさい。
あ、そうなんですね。わかりまし
すいま
た。
はい。
そうですね。
なので、他に
let
質
me,
問ある方いるのはい。
let me ask a questions.
Yes, thank you.
I found your approach to retrieval method for robot learning for very interesting, I think. So, I have a quick questions regarding to existing approach.
Yes.
Could you please explain once more why
Mhm.
distance-based retrieval leads to high variance?
Yes. So I would say so. I think this a figure on the right is quite important here to show. So for example, here when you use L2 distance, so the bright color here is the target data that we want, and then here the 2 points that it retrieves is the prior data based on distance. But actually, if you there may be other points here that is like relevant and in the same distribution to the target data, but it's not retrieved because it's only using L2 distance, right? But on the contrary, if you use probability density here, it can actually estimate that this kind of a cluster of data is actually useful to learn this target data point. And I think that's kind of like why it leads to high variance, because even if it's like a closer sample, there's no guarantee that it will be actually helpful for the policy learning. So the this kind of probabilistic method gives you a better information on if the data points will be in the same task distribution or not. Yeah, so I think that's kind of the short answer on if it helped on why it leads to high variance. Yeah.
Thank you for your answers.
Yeah.
Sounds great.
Yeah.
それでは他に質問はないでしょうか。はい。なければ、本発表はこれで終わりたいと思います。